Welcome to the Explainer. Acid-based equilibria? Yeah, it's a huge topic, right? So today, we're going to build the ultimate toolkit for Chapter 14. We'll pack it with all the essentials, the vocabulary, the formulas, and the main ideas. Everything you need to really nail this.
Okay, so how are we going to build this toolkit? Well, first things first, you got to speak the language, right? So we'll start with the key vocabulary. Then we'll grab the mathematical tools, the equations that do all the heavy lifting. And finally, we'll see how to actually use all this stuff.
So, why all the fuss about this one chapter? I mean, this quote really says it all. We're talking about chemistry that explains everything from how sinkholes form to how your own body transports oxygen. It's literally everywhere. So yeah, it's a big deal. Let's start building that toolkit, and we'll begin with the language.
All right, first tool in the box, vocabulary. We're about to flash all 31 key terms on the screen over the next couple of slides. Now, I'm not going to read every single one, so this is the perfect time to hit pause whenever you need to, and just make sure you've got these definitions down cold. Okay, here's our first set of terms. These are really the fundamentals. What it means for an acid to ionize, how we define an acidic solution, and that super interesting concept of things like water being able to play both sides as an acid and a base.
Now this next group of words, this is where we really get to the heart of it. You've got the Bronsted-Lowry definitions, acids donate protons, bases accept them. Super simple, but super powerful. And we get our first look at buffers, which, trust me, are a total game changer when it comes to controlling pH.
Here we're getting a bit more detailed, right? We're classifying acids based on how many protons they can give away. Monoprotic, diprotic, and so on. And hey, this slide even gives us a little preview of the math to come, defining some key constants, and yep, there it is, the Henderson-Hasselbalch equation.
And to wrap up our vocabulary, here are the terms we need for measurement and analysis. This is where we define those crucial scales, pH and pOH, and get the language for the hands-on lab stuff, like titrations. All right, language part, check. Now it's time to add the power tools to our kit, the key equations. These are the formulas you're going to use to actually calculate things and predict what happens in a solution. And just like before, feel free to pause and really soak these in.
So this first batch of equations, this is all about the basics of water and pH. You've got Kw, the constant that governs water's behavior, then the formulas for jumping back and forth between ion concentration and the pH scale, and of course, the classic definition of Ka, which tells us how strong an acid is.
Okay, next up we've got the tools for bases, with the Kb expression looking pretty similar to K, right? We also see that really cool relationship between K and Kb for a conjugate pair. And there it is again, the star of the show for buffers, the Henderson-Hasselbalch equation. That's your best friend for buffer calculations.
Okay, so we've got the language, we've got the tools. Now for the fun part, how do we actually use all this? Let's do a quick run through of the chapter, section by section, and see how it all connects.
First up, section 14.1. This really just sets the stage. It's all about that Bronsted-Lowry definition, which is the framework for the whole chapter. Acids are proton donors, bases are proton acceptors. That simple proton handoff is what creates those conjugate pairs we hear so much about.
Then, in 14.2, we get our measuring sticks, the pH and pOH scales. And the most important thing to remember here is that pH is logarithmic. So a pH of 2 isn't just one step away from a pH of 3, it's 10 times more acidic. It's a really clever way to handle massive differences in concentration.
Next, 14.3 teaches us how to compare the strengths of different acids and bases. It's all about those ionization constants, Ka and Kb, and some trends on the periodic table. But the big takeaway, the one you absolutely have to remember, is that inverse relationship. The stronger the acid, the weaker its conjugate base, and vice versa.
Okay, section 14.4, hydrolysis of salts. This is a super important point. It's not just the obvious acids and bases that can change a solution's pH. When you dissolve a salt in water, sometimes its ions react with the water. That's all hydrolysis is, and that can make the solution acidic or basic.
Then we've got 14.5, which is all about polyprotic acids. These are the acids that have more than one proton to give away. The big idea here is that they don't lose them all at once. It's a step-by-step process, and each step is harder than the last, which means each ionization is weaker than the one before it.
Now, buffers, from section 14.6, this is a huge concept, not just in chem but in biology too. Think of them like chemical shock absorbers.
They're these special mixtures that resist big pH changes, keeping things stable even when you add a little acid or base.
And last but not least, section 14.7 takes us into the lab with acid-base titrations. This is all about the actual technique you'd use to figure out the concentration of an unknown solution. You carefully add a solution you do know, track the pH, and the resulting graph gives you the answer.
So there you have it, a super fast review of Chapter 14. Your toolkit is officially loaded up with the language, the equations, and the core ideas. So I'll just leave you with this question. Now that you've got this toolkit, where do you see acid-base chemistry playing a role in your day-to-day life? Because once you start looking, you'll see it's everywhere.